Hi, this is Cletus, and I'm going to present my thesis on the topic control of clay swelling in montmorillonite and kaolinite clay minerals by precipitation of magnesium hydroxide between clay layers. So, as the title repeats the word clay, which is an abundant resource on Earth, uh, and one of the predominant property of clay is swelling. And the problem addressed in this thesis is instability in wellbore due to clay swelling. And that is because when untreated water in the form of drilling fluid comes in contact with the clay in the wellbore or the water in the formation in the rocks, such as the formation water in the rocks comes in contact with the clay tends to swell, and this swelling breaks and falls into the wellbore, which affects the drilling operation by damaging the drill bit and also collapses the wellbore, which has significant economic loss to oil and gas industry. To get in touch with the problem in depth, it's good to know about the clay mineralogy and swelling mechanism. So the predominant clay minerals are kaolinite, montmorillonite, and alite, out of which kaolinite is a non-swelling clay mineral where the layers of clay attached by hydrogen bonds, and it's pretty hard to break. In case of montmorillonite, which is known for swelling, the two layers of clay are attached by weak van der Waals forces, and it's easy to break by a molecule of water. In case of alite, which are bonded by the potassium ions, probably leaching of potassium ions leads to the swelling of alite clay mineral. So, why does montmorillonite, or how does swelling occurs in montmorillonite? And that's because of intercrystalline, or known as cation exchange effect. So, what exactly happens in a layer of montmorillonite clay mineral? Uh, it has a TOD structure, such as silica, alumina, and silica. And when this layer of clay comes in contact with water, the alumina gets replaced by magnesium ions, and thus significantly forming a layer of negative charge in the outer surface of the layer, which attracts either sodium ions or calcium ions or potassium ions. And based on the type of ions attached, it's called sodium montmorillonite or calcium montmorillonite, and it's pretty evident that sodium has high hydration capacity because it has higher spacing in the interlayers compared to montmorillonite, and therefore it's evident that calcium montmorillonite swells lesser compared to sodium montmorillonite. So is there a solution to this problem? Yes, there is a solution to this problem in the form of swelling inhibitors. So in the oil and gas industry, potassium chloride, an inorganic salt, is used as an swelling inhibitor to address the swelling issues in the wellbore. As you could see in the figure 4, where a swollen clay, a clay is swollen because of water molecules in between its layers, and when it's treated with KCl, the potassium ions replaces um, the ions in between the clay layers and reducing the height of the clay, and thus inhibiting its swelling. In this thesis, we will be discussing about magnesium hydroxide as a potential swelling inhibitor, where in the lab, Dr. Patel did identify magnesium hydroxide as an effective swelling inhibitor by precipitating magnesium hydroxide between the layers of clay. So the objective of this thesis is to analyze different methods and examine the conditions, like when talk about methods, to use a wild test and swellometer methods and examine several conditions that impact the control of clay swelling in bentonite and kaolinite clay. So what are the objectives? The first thing is to know what quantity of reagents are required to precipitate magnesium hydroxide effectively, and what's the aging time, and to use XRD to examine the various conditions, and also out of the two methods, what's the swelling pattern? Is it same or different? A quick description of the thesis approach. So stage 1, I did study the minerals, and stage 2 applied the methods to examine the conditions and interpreted the results using XRD, and the results are being discussed as follows. So before heading to the results, a quick insight on precipitation of magnesium hydroxide on clay structure and how this happens. Zacchaeus was one of the first person to go and give a heads up that magnesium hydroxide precipitation on smectite resulted in swelling inhibition of smectite clay mineral. So what happens in a structure of montmorillonite, in this case bentonite, is when you treat it with magnesium salt and sodium hydroxide, the layers in between the clay changes and it forms a brucite layer where magnesium reacts with hydroxide forming a strong brucite-like layer, and this structure resembles a chloride structure, which is a non-swelling clay structure, and that's how montmorillonite gets converted to chloride by precipitation of magnesium hydroxide between the clay layers. And Zacchaeus did identify 1.5 as a suitable molar ratio for magnesium hydroxide precipitation. Swelling index is again a key parameter to measure swelling, and as the equation says, it's the final height minus initial height divided by the final by the initial height of the sample in mm. To put it in context, swelling index of 1 means 100% of increase in the height of given sample, and of course there's a little bit of uncertainty because of the wild test method being used, and it's calculated as plus or minus 0.1. So one of the prominent findings of the thesis was the quantity of reagent. So from literature, I was able to identify that 16 MEq of magnesium hydroxide per gram of clay is effective enough to precipitate magnesium hydroxide in the interlayer of the clay mineral to inhibit swelling. So in this case, I did consider 1.4 as a suitable molar ratio to inhibit swelling of bentonite when treated in formation water, and on calculating we did identify 24.6 milliequivalent of magnesium hydroxide per gram of clay, which is a little bit higher than 16 MEq, and this accounts for the precipitation of magnesium hydroxide in the internal layers as well as the outer layers of the clay structure, yielding a swelling index as low as 0.08. And the next finding was to identify what is the aging time for an effective precipitation, in which swelling index was plotted against aging time for different molar ratios of magnesium hydroxide, bentonite, precipitated magnesium hydroxide, out of which you could very well see at 24 hours is when the swelling index was least for 1.4 molar ratio, and this was again seen effectively when the aging time was fixed for different molar ratios. So that's how an aging time of 24 hours was decided as effective for precipitation. And in the slide on the rate of swelling, in which swelling index of untreated bentonite and swelling index of bentonite treated with 4% KCl and swelling index of magnesium hydroxide at 1.4 molar ratio was plotted against swelling duration, and it's identified that magnesium hydroxide precipitated bentonite had the least rate of swelling. So this slide gives a quick insight of what happens at different OH by mg molar ratios of bentonite being precipitated with magnesium hydroxide. So on increasing the molar ratio of magnesium hydroxide precipitation, it was identified that the swelling index increased gradually. This was because of decrease in magnesium concentration, and beyond 8 there was a sudden dip, and this resembles probably beyond 8 magnesium hydroxide started forming, by which swelling was inhibited, resulting in reduced swelling index. However, the result was dissimilar with Dr. Patel's findings, and this might be because of different clay samples being used in the study and different soaking and aging time being adopted. And In the XRD results for different OH by mg molar ratio, 1.4 we did identify um, uh, the composition as similar to a chloride, and as the molar ratio increases, we could see evolutions of new minerals, and beyond 8 we could see the composition coming back in shape with the OH with 1.4 molar ratio. So the findings from this graph is when we change the pH of formation water, at higher pH is low of swelling because of increase in NA+ cations neutralizes the negative charge of clay sheets, and in replenishment you could see a drop in swelling at higher swelling index because of reverse osmotic effect. And in case of kaolinite, negative swelling was observed, and this is mainly because of the limitation of the wild test method itself, whereas positive swelling was observed with when treated with magnesium hydroxide. And this was strange because, and it might be because of the different quantity of reagent used. On comparing wild test method with swellometer, similar results were observed in both the patterns. So I'm transitioning this to industrial application. So bentonite-rich montmorillonite is pretty efficient as in drilling fluid, and in kaolinite, precipitated magnesium hydroxide has to be researched whether it could prevent fines migration. So to conclude, the thesis did identify the effective quantity of reagents for magnesium hydroxide precipitation in formation of water, and it was pretty much predominant that the rate of swelling was low compared to other swelling inhibitor, and similar swelling pattern was observed between wild test and swellometer. So in case of montmorillonite, further research could be done to identify the precise quantity of reagents required for both internal and external clay layer swelling. And in case of kaolinite, kaolinite does swell in alkali solutions, so probably if kaolinite treated with magnesium hydroxide could prevent the swelling, it has to be researched further, and also fines reduction of fines migration of kaolinite precipitated magnesium hydroxide could be researched further. So, yep, that's it. Thank you.